In the vast darkness of interstellar space, countless objects drift between star systems, carrying with them the secrets of distant worlds and ancient cosmic events. Most of these wanderers remain invisible to us, passing through our solar system undetected or traveling trajectories that never bring them close enough for observation. But on a summer day in July 2025, astronomers made a discovery that would add another chapter to our understanding of these mysterious visitors from beyond. The discovery of 3I/ATLAS represents only the third time in recorded human history that we have identified an interstellar object passing through our solar system, making it an extraordinarily rare and scientifically valuable find. The story of 3I/ATLAS begins with the Asteroid Terrestrial Impact Last Alert System, commonly known as ATLAS, a global network of 4 robotic telescopes positioned strategically across Hawaii, Chile, and South Africa. These automated sentinels continuously scan the night sky, systematically surveying nearly the entire visible sky every 24 hours in their primary mission to identify near-Earth objects that could potentially pose an impact threat to our planet. On July 1, 2025, the ATLAS survey telescope stationed at Rio Hurtado, Chile, captured what initially appeared to be just another faint, fast-moving point of light against the star-filled background of the constellation Sagittarius. The object was approximately 670 million kilometers from the Sun at the time of discovery, traveling at an extraordinary speed that would soon reveal its true nature. The initial observations of what would later become known as 3I/ATLAS were submitted to the International Astronomical Union's Minor Planet Center under the temporary designation A11-3Z. At first glance, the object's trajectory suggested it might be on a highly eccentric path that could potentially bring it close to Earth's orbit, leading to its temporary placement on the Near-Earth Object Confirmation page until astronomers could gather enough data to determine its precise orbital characteristics. However, as follow-up observations began pouring in from observatories around the world, involving both professional astronomers and dedicated amateur observers, a very different picture started to emerge. The key to understanding 3I/ATLAS lay in its remarkable velocity and trajectory. Initial measurements showed the object was moving at approximately 60 kilometers per second relative to the Sun, a speed that far exceeded what would be expected for any object bound by our solar system's gravitational field. This hyperbolic velocity indicated that the object was moving too fast to be captured by the Sun's gravity, meaning it was following an unbound, open-ended trajectory that would carry it past our star and back into the depths of interstellar space. The confirmation came when astronomers calculated the object's orbital eccentricity, finding it to be an extraordinarily high 6.141, making its trajectory appear relatively straight rather than curved. To put this in perspective, objects with elliptical orbits bound to our solar system have eccentricities less than 1, while hyperbolic interstellar objects have eccentricities greater than 1. Pre-discovery observations and early activity. One of the most fascinating aspects of 3I/ATLAS is the wealth of pre-discovery observations that astronomers were able to uncover once they knew what to look for. These archival images, recovered from the databases of multiple survey systems, extended the observation timeline back significantly and provided crucial data about the object's behavior before its official discovery. The Zwicky Transient Facility at Palomar Observatory captured images of 3I/ATLAS on June 28 to 29, 2025, just hours before the official discovery report, as well as earlier observations dating back to June 14 to 21, 2025. Additional ATLAS observations from June 25 to 29 were also identified, and dedicated amateur astronomer Sam Dean noted even earlier ATLAS observations extending back to June 5 to 25, 2025. Perhaps most remarkably, NASA's Transiting Exoplanet Survey Satellite, TESS, had been observing 3I/ATLAS nearly continuously from May 7 to June 2, 2025, without astronomers initially realizing what they were looking at. Using sophisticated shift-stack methods to create deep composite images, researchers were able to recover the object from the TESS data, revealing that 3I/ATLAS had an average TESS magnitude of 19.6 and an absolute visual magnitude of 12.5, measurements that were remarkably consistent with observations made in July after its official discovery. This consistency suggests that 3I/ATLAS may have been displaying active comet-like behavior as far out as 6.4 astronomical units from the Sun, much farther than would typically be expected for cometary activity. The reason 3I/ATLAS wasn't discovered earlier, despite being captured in multiple survey images, likely relates to its position in the sky during those early observations. Amateur astronomer Sandin suspected that the comet was not identified sooner because it was passing in front of the galactic center's dense star fields, where the comet would be extremely difficult to distinguish from the countless background stars. This highlights both the challenges of detecting interstellar objects and the importance of multiple survey systems working in concert to identify these rare visitors. Physical characteristics and size. Determining the exact size and physical characteristics of 3I/ATLAS has proven to be one of the most challenging aspects of studying this interstellar visitor. Unlike asteroids, which appear as simple points of light, active comets are surrounded by a diffuse coma of gas and dust that makes it difficult to distinguish where the nucleus ends and the surrounding material begins. Early estimates suggested that 3I/ATLAS could be quite large, potentially 10 to 20 kilometers in diameter, which would make it significantly larger than the previous two known interstellar objects. However, more recent observations using the Hubble Space Telescope have provided a clearer picture of the object's true size. The Hubble observations, which represent some of the sharpest images yet obtained of 3I/ATLAS, suggest that the diameter of the comet's nucleus is actually much smaller than initially estimated, likely between 0.32 and 5.6 kilometers, with the most probable diameter being less than 1 kilometer. This dramatic revision downward in size estimates illustrates both the challenges of studying active comets and the importance of high-resolution observations in determining accurate physical properties. The apparent brightness of 3I/ATLAS, which initially led to size estimates of 10 to 15 kilometers, appears to be due more to its active coma and the light-scattering properties of the dust and gas surrounding the nucleus, rather than the size of the solid nucleus itself. Despite the uncertainty in its exact dimensions, 3I/ATLAS is notable for being the brightest interstellar object detected to date. The comet reached a magnitude of around 20 at the end of May 2025 and had brightened to between 17.7 and 17.8 magnitude in the ATLAS O-band by the time of its discovery. This brightness, combined with what appears to be a relatively flat light curve showing only 0.2 magnitude of brightness variation throughout its approximately 29-hour rotation period, suggests that the nucleus may have a relatively uniform shape or composition compared to the more irregular 1I/Oumuamua. Rotational properties and light curve analysis. The rotational characteristics of 3I/ATLAS have provided astronomers with valuable insights into the object's physical structure and formation history. Through careful photometric monitoring over multiple nights, researchers have identified a rotation period of approximately 29 hours, though this measurement still requires further observations to constrain it more precisely. This rotation period is significantly longer than what has been observed for most asteroids and comets in our solar system, which typically rotate much faster due to various evolutionary processes, including collisions and tidal interactions. What makes the rotation of 3I/ATLAS particularly intriguing is the minimal variation in brightness observed throughout its rotation cycle. Unlike many asteroids and comets that show dramatic changes in brightness as different phases are presented to observers, 3I/ATLAS exhibits only about 0.2 magnitude of variation over its 29-hour period. This relatively flat light curve could indicate several possibilities about the object's shape and composition. It might suggest that the nucleus is relatively spherical rather than elongated, or it could indicate that the surface composition is remarkably uniform across different regions of the object. The TESS observations, which provided nearly continuous monitoring over several weeks, revealed no statistically significant evidence of the nucleus rotation period in their data. This could be due to the long rotation period combined with the relatively subtle brightness variations, making it difficult to detect the rotational signal against the background noise and systematic effects in the data. However, the TESS observations did provide valuable confirmation that the object maintained consistent brightness levels over extended periods, supporting the idea that 3I/ATLAS has been in a relatively stable state during its passage through the inner solar system. Spectroscopic analysis and composition. Understanding the composition of 3I/ATLAS provides crucial insights into the conditions and processes that shaped it in its original star system billions of years ago. Spectroscopic observations using the Goodman high-throughput spectrograph on the 4.1-meter SOAR telescope in Chile have revealed a reflectance spectrum covering wavelengths from 3,700 to 7,000 angstroms. The spectrum shows a distinctly red continuum that is comparable to what astronomers observe in extreme trans-Neptunian objects in the outer reaches of our own solar system, suggesting similar surface compositions dominated by complex organic materials. The red coloration observed in 3I/ATLAS is particularly significant because it indicates the presence of complex carbonaceous and irradiated organic compounds on the surface. This reddish hue is thought to result from long-term exposure to cosmic radiation and solar wind particles, which gradually alter the chemical structure of organic materials on the surface of objects in space. The presence of these materials suggests that 3I/ATLAS formed in the cold outer regions of its original star system, far from its parent star where volatile ices and organic compounds could condense and survive. Observational campaigns and visibility. The discovery of 3I/ATLAS has triggered an intensive international observational campaign involving telescopes and instruments around the world. The rarity of interstellar objects, with only 3 confirmed examples in recorded history, means that every opportunity to study these visitors provides irreplaceable scientific data about conditions and processes in other star systems. The observational window for 3I/ATLAS is relatively limited, as the comet will only remain visible to ground-based telescopes through September 2025, after which it will pass too close to the sun's glare to observe safely. Professional observatories have dedicated hundreds of hours of telescope time to studying 3I/ATLAS, using a wide range of instruments and techniques. High-resolution imaging campaigns aim to resolve details of the coma structure and any jets or other features that might indicate active regions on the nucleus surface. Spectroscopic observations across different wavelength ranges are being used to identify the composition of both the nucleus and the material being released into the coma. Photometric monitoring programs track changes in brightness and color as the comet evolves during its approach to the sun. The Hubble Space Telescope has played a particularly important role in characterizing 3I/ATLAS, providing some of the sharpest images yet obtained of the object. These high-resolution observations are crucial for separating the light from the nucleus itself versus the surrounding coma, enabling more accurate size determinations and studies of the nucleus composition. Ground-based observations complement the space-based data by providing continuous monitoring over longer time periods and access to wavelength ranges that may be blocked by Earth's atmosphere when observing from space. After September 2025, 3I/ATLAS will disappear behind the Sun from Earth's perspective, but it is expected to reappear on the other side by early December, allowing for renewed observations as it begins its journey back toward interstellar space. These post-perihelion observations will be particularly valuable for studying how the comet's activity evolves as it moves away from the Sun and begins to cool down again. Age estimates and origin. One of the most remarkable aspects of 3I/ATLAS may be its extraordinary age. Preliminary estimates suggest that this interstellar wanderer could be between 3 and 11 billion years old, potentially making it the oldest comet ever observed. These age estimates are derived from relationships between the orbital characteristics of interstellar objects and the time required for gravitational interactions in stellar systems to accelerate objects to the observed velocities. If these estimates prove correct, 3I/ATLAS would be at least 30 times older than 1I/Oumuamua and approximately 3 times older than 2I/Borisov. The ancient age of 3I/ATLAS, if confirmed, would have profound implications for our understanding of planetary system formation and evolution. An object that has been drifting through interstellar space for billions of years would have formed during the early epochs of our galaxy's history, when star formation rates were higher and the chemical composition of stellar systems was different from what we observe today. Such an object would carry within its composition a record of the materials and conditions present in stellar nurseries billions of years ago, providing a unique window into the early history of planetary system formation. The preservation of volatile ices and organic compounds in an object of such great age raises interesting questions about the processes that have affected 3I/ATLAS during its journey through interstellar space. While the cosmic radiation environment and occasional encounters with interstellar gas clouds would gradually alter surface materials, the interior of the object could potentially preserve pristine samples of ancient solar system materials. This makes 3I/ATLAS not just a visitor from another star system, but potentially a messenger from the distant past of our galaxy. Scientific significance and comparative analysis. The discovery and study of 3I/ATLAS contributes to a growing database of interstellar object characteristics that is beginning to reveal patterns and differences among these rare visitors. Each of the 3 known interstellar objects has displayed unique properties that provide different insights into the processes that shape and eject material from planetary systems. 1I/Oumuamua was notable for its highly elongated shape and unusual acceleration that could not be explained by gravitational forces alone, leading to extensive debates about its composition and nature. 2I/Borisov appeared more like a typical solar system comet in its behavior and composition, suggesting that some interstellar objects may be quite similar to the comets we see in our own system. 3I/ATLAS adds another data point to this small but growing sample, with characteristics that both resemble and differ from its predecessors. Like 2I/Borisov, it displays clear cometary activity with a visible coma and evidence of volatile outgassing. However, its much higher velocity, earlier onset of activity, and unique spectroscopic properties distinguish it from both previous interstellar visitors. The red coloration and lack of obvious gas emission lines in its spectrum suggest a composition and evolutionary history that may be distinct from both 1I/Oumuamua and 2I/Borisov. The study of interstellar objects like 3I/ATLAS provides unique opportunities to investigate the formation and evolution of planetary systems beyond our own solar system. Unlike exoplanets, which can only be studied through their gravitational effects on their host stars or through the analysis of starlight that has passed through their atmospheres, interstellar objects can potentially be analyzed using all the techniques available for studying solar system bodies. This includes detailed spectroscopy, high-resolution imaging, and potentially even future spacecraft missions that could provide in situ measurements of composition and structure. Implications for planetary system formation. The characteristics observed in 3I/ATLAS provide valuable constraints on models of planetary system formation and evolution. The high velocity of the object suggests that it was ejected from its parent system through a violent gravitational encounter, likely involving massive planets or stellar companions. The efficiency of such ejection processes and the resulting velocity distributions of ejected objects depend on the architecture and dynamics of the planetary system, providing indirect information about the types of systems that are effective at producing interstellar objects. The composition of 3I/ATLAS, with its red coloration and organic-rich surface materials, suggests formation in the cold outer regions of a planetary system where such materials can condense and survive. This is consistent with models that predict most ejected objects should originate from the outer regions of planetary systems, where gravitational encounters with giant planets are most likely to provide the energy needed to escape the system entirely. The preservation of volatile ices, even at relatively large distances from the Sun, indicates that 3I/ATLAS formed in an environment cold enough to allow these materials to remain stable. The age estimates for 3I/ATLAS, if confirmed, would provide constraints on the timescales over which planetary systems remain dynamically active and continue ejecting material into interstellar space. An object ejected 3 to 11 billion years ago would have originated from a stellar system during an era when such systems were likely still undergoing significant evolutionary changes, including late heavy bombardment periods and migration of giant planets. Understanding when and how objects like 3I/ATLAS were ejected helps astronomers model the long-term evolution of planetary systems and predict the population of interstellar objects that should be observable today. Detection challenges and survey improvements. The discovery of 3I/ATLAS highlights both the capabilities and limitations of current astronomical survey systems. While the ATLAS network successfully detected the object, the fact that it appeared in multiple survey images weeks before its official discovery illustrates the challenges involved in identifying interstellar objects among the vast numbers of moving objects detected by automated systems. The position of 3I/ATLAS in front of the dense star fields of the galactic center made it particularly difficult to distinguish from background stars, demonstrating how observational circumstances can significantly affect detection efficiency. The success in recovering pre-discovery observations of 3I/ATLAS from multiple survey systems shows the value of maintaining comprehensive archives of astronomical data. These archival observations not only extended the timeline available for orbital determination but also provided crucial early data about the object's brightness and activity levels. The ability to search through these archives after discovering an interesting object has become an essential tool for maximizing the scientific return from interstellar object encounters. Future improvements to survey systems may enhance our ability to detect interstellar objects earlier and more reliably. This includes developing better algorithms for distinguishing interstellar objects from solar system objects based on their motion patterns, improving the sensitivity and coverage of survey telescopes, and implementing faster follow-up procedures to confirm interesting detections. The experience gained from studying 1I/Oumuamua, 2I/Borisov, and now 3I/ATLAS is helping astronomers refine these techniques and prepare for future discoveries. Future observations and mission possibilities. As 3I/ATLAS continues its journey through the solar system, astronomers are planning extensive observational campaigns to maximize the scientific return from this rare opportunity. The period leading up to perihelion in late October 2025 will be particularly important for spectroscopic studies, as the increasing solar heating should trigger more intense cometary activity and make it easier to detect and analyze the gases being released from the nucleus. These observations will help determine the inventory of volatile compounds present in the object and compare them to the materials found in solar system comets. The post-perihelion period, when 3I/ATLAS reappears from behind the Sun in December 2025, will provide opportunities to study how the object's activity evolves as it begins to cool and recede from the Sun. These observations may reveal different volatile compounds that are released at different temperatures, providing a more complete picture of the object's composition. The changing geometry as the comet moves away from the Sun will also allow astronomers to study different aspects of the coma and tail structure. While no spacecraft missions to 3I/ATLAS are currently planned or feasible given the short lead time and high velocity of the object, the experience of studying this interstellar visitor is providing valuable lessons for future mission planning. The high velocities and unpredictable arrival times of interstellar objects present significant challenges for spacecraft missions, but the scientific value of in situ measurements would be enormous. Future space agencies may need to develop rapid response mission capabilities or maintain spacecraft in standby configurations that could be quickly redirected to intercept newly discovered interstellar objects. The broader context of interstellar objects, the discovery of 3I/ATLAS contributes to our growing understanding of the population and characteristics of interstellar objects in our galactic neighborhood. Statistical models based on the discovery rate of these objects suggest that there should be thousands or even millions of interstellar objects passing through the solar system at any given time. But most are too small or too faint to detect with current survey capabilities. The fact that we have now discovered 3 interstellar objects in less than a decade suggests that improved survey systems are beginning to reveal this previously hidden population. Each new interstellar object discovery helps refine estimates of the total population and provides constraints on models of planetary system formation and evolution throughout the galaxy. The diversity observed among the 3 known objects, from the mysterious 1I/Oumuamua to the comet-like 2I/Borisov to the ancient and fast-moving 3I/ATLAS, suggests that interstellar space contains a rich variety of objects with different formation histories and compositions. This diversity reflects the wide range of planetary system architectures and evolutionary processes that have operated throughout galactic history. The study of interstellar objects also provides a unique form of galactic archaeology, allowing astronomers to investigate the materials and processes that were operating in stellar systems at different epochs in galactic history. Objects like 3I/ATLAS, with their potentially ancient ages, serve as time capsules that preserve samples of materials from the early universe. As more interstellar objects are discovered and studied, astronomers will be able to build up a statistical picture of how planetary system formation and evolution has changed over cosmic time. Technological and methodological advances. The study of 3I/ATLAS has benefited from significant advances in astronomical technology and data analysis techniques that were not available during the discovery of 1I/Oumuamua. The use of machine learning algorithms to search through archival survey data has enabled the recovery of pre-discovery observations that extend the observational baseline and improve orbital determinations. Advanced image processing techniques, including the shift and stack methods used to recover 3I/ATLAS from TESS data, allow astronomers to extract meaningful measurements from observations that might otherwise be dismissed as too faint or noisy. Interestingly, despite showing clear evidence of cometary activity through its visible coma, spectroscopic observations taken when 3I/ATLAS was at a heliocentric distance of 4.4 astronomical units detected no discernible gas emission from the canonical cometary species that astronomers typically look for, including CN, C3, C2, CO+, and forbidden oxygen lines. This absence of obvious gas emission signatures creates something of a paradox. The object clearly has a coma indicative of active sublimation processes, yet the expected spectroscopic tracers of this activity are not visible. This could suggest that either the sublimation is occurring at such low levels that the gas emissions are below the detection threshold, or that 3I/ATLAS is releasing dust through other mechanisms such as thermal fracturing or electrostatic effects. Cometary activity and coma development. One of the most distinctive features that sets 3I/ATLAS apart from the first interstellar object, 1I/Oumuamua, is its clear display of cometary activity. Unlike 1I/Oumuamua, which appeared as a simple point of light with no visible coma or tail throughout its passage through the solar system, 3I/ATLAS began showing signs of a diffuse coma shortly after its discovery, confirming its classification as an active comet rather than an inert asteroid. This cometary activity is created by the sublimation of volatile ice on and near the surface of the nucleus as the object approaches the Sun and receives increasing amounts of solar heating. The development of the coma around 3I/ATLAS has been particularly interesting to observe because it began manifesting when the comet was still quite far from the Sun, at distances of 4 to 5 astronomical units. For comparison, most comets from our own solar system don't begin showing significant activity until they reach distances of 2 to 3 astronomical units from the Sun. This early onset of activity suggests that 3I/ATLAS contains highly volatile ices that sublimate at lower temperatures than the water ice that dominates most solar system comets, or that the object has other properties that make it more susceptible to solar heating effects. As 3I/ATLAS continues its approach toward perihelion, which will occur around October 30, 2025, at a distance of approximately 1.36 astronomical units from the Sun, astronomers expect the cometary activity to intensify significantly. The comet will develop a more prominent tail as solar radiation pressure and the solar wind push the released dust and gas away from the nucleus in the direction opposite to the Sun. This increasing activity will provide valuable opportunities for detailed spectroscopic studies to identify the specific volatile compounds being released and to better understand the composition and structure of this interstellar visitor. Trajectory and future path. The trajectory of 3I/ATLAS through our solar system follows an extremely hyperbolic path that carries it on a one-way journey past the Sun and back into interstellar space. When the object entered our solar system, it was moving at a hyperbolic excess velocity of 58 kilometers per second relative to the Sun, making it the fastest-moving interstellar object yet discovered. This speed is significantly higher than the previous interstellar visitors. 1I/Oumuamua had a hyperbolic excess velocity of 26 kilometers per second, while 2I/Borisov moved at 32 kilometers per second. The extreme velocity of 3I/ATLAS provides important clues about its origin and the circumstances that ejected it from its parent star system. Objects don't naturally achieve such high velocities without experiencing significant gravitational interactions, suggesting that 3I/ATLAS was likely involved in a dramatic encounter with one or more massive objects in its original system. This could have involved close encounters with giant planets similar to Jupiter or Saturn, gravitational interactions during stellar encounters between binary star systems, or even more exotic scenarios involving stellar explosions or black hole interactions. The comet's closest approach to the Sun will occur on October 29 to 30, 2025, at a distance of 1.36 astronomical units, placing it roughly between the orbits of Earth and Mars. Throughout its passage, 3I/ATLAS will maintain a safe distance from Earth, never coming closer than 1.8 astronomical units, or approximately 270 million kilometers. After its solar encounter, the comet will begin its journey back toward interstellar space, gradually slowing as the Sun's gravity pulls back on it, but never slowing enough to be captured into a bound orbit. Improvements in spectroscopic instruments and observational techniques have enabled more detailed compositional studies than were possible with earlier interstellar objects. The ability to obtain meaningful spectra of such faint and distant objects requires sophisticated instrument designs and careful observational planning to maximize signal-to-noise ratios while minimizing systematic effects. The combination of ground-based and space-based observations provides complementary data that helps overcome the limitations of any single observational approach. The rapid communication and coordination among observatories worldwide has also improved dramatically since the discovery of Oumuamua. The ability to quickly share discovery information and coordinate follow-up observations among dozens of telescopes and research groups maximizes the scientific return from these brief encounters with interstellar visitors. This international collaboration demonstrates the value of maintaining strong connections among the global astronomical community for responding to time-critical discoveries, theoretical implications, and models. The high velocity and other characteristics of 3I/ATLAS provide important tests for theoretical models of how objects are ejected from planetary systems and how they evolve during their journey through interstellar space. The velocity distribution of interstellar objects depends on the efficiency of different ejection mechanisms and the typical energy scales involved in planetary system dynamics. Objects ejected by planetary encounters should have a different velocity distribution than those ejected by stellar encounters or other more exotic mechanisms. The preservation of volatile ices in 3I/ATLAS during what may be billions of years in interstellar space provides constraints on models of how objects evolve in the interstellar environment. While the cosmic ray radiation field and occasional encounters with interstellar gas clouds should gradually erode and alter surface materials, the interior of the object should remain largely unaffected. The fact that 3I/ATLAS still contains sufficient volatile material to drive cometary activity suggests that interstellar objects can preserve pristine samples of their original compositions over very long timescales. The compositional similarities between 3I/ATLAS and objects in the outer solar system support models that suggest similar formation processes operate in planetary systems throughout the galaxy. The red coloration and organic-rich composition observed in 3I/ATLAS resembles what is seen in Kuiper belt objects and other trans-Neptunian objects in our own solar system, suggesting that the cold outer regions of planetary systems commonly produce objects with similar characteristics regardless of the specific details of the host star system. Future prospects and discoveries. The successful discovery and characterization of 3I/ATLAS demonstrates that current survey systems are beginning to routinely detect interstellar objects, suggesting that more discoveries are likely in the coming years. The upcoming Legacy Survey of Space and Time (LSST) at the Vera Rubin Observatory is expected to dramatically increase the rate of interstellar object discoveries, potentially finding dozens or hundreds of such objects over the course of its planned operation. This will transform the study of interstellar objects from investigating isolated examples to conducting statistical studies of populations and distributions. Future space missions, specifically designed to study interstellar objects, may become feasible as our ability to predict and track these objects improves. The European Space Agency has already studied concepts for rapid response missions that could be launched to intercept newly discovered interstellar objects, though the technical challenges remain formidable. Alternative approaches might involve maintaining spacecraft at strategic locations in the outer solar system, where they could be redirected to study passing interstellar objects with shorter lead times. The integration of interstellar object studies with other areas of astronomy, including exoplanet research and galactic archaeology, will likely become increasingly important as the field matures. The materials and formation processes revealed by studying interstellar objects provide direct constraints on models of planetary system formation that complement the statistical information available from exoplanet surveys. This multifaceted approach to understanding planetary systems will help astronomers develop more complete and accurate models of how planetary systems form and evolve throughout the galaxy. Scientific legacy and continuing questions. The study of 3I/ATLAS continues a tradition of groundbreaking discoveries that have fundamentally changed our understanding of the solar system and its place in the galaxy. Just as the discovery of the first exoplanets revealed that planetary systems are common throughout the galaxy, the discovery of interstellar objects has shown that these systems regularly exchange material through ejection and capture processes. Each new interstellar object provides additional pieces of the puzzle that is slowly revealing the complex history of planetary system formation and evolution on galactic scales. Many fundamental questions about 3I/ATLAS and interstellar objects in general remain unanswered and will require continued observations and analysis to resolve. The exact size, composition, and internal structure of 3I/ATLAS are still uncertain and will benefit from additional high-resolution observations and spectroscopic studies. The age estimates, while intriguing, are based on theoretical models that make assumptions about ejection mechanisms and galactic dynamics that may not apply to this specific object. The origin of 3I/ATLAS, which stellar system it came from, and what processes ejected it into interstellar space, may never be definitively determined, but continued study of its composition and trajectory may provide clues about the types of environments that produce such objects. The comparison of 3I/ATLAS with future interstellar object discoveries will help determine whether its characteristics are typical or exceptional among the population of objects drifting through our galactic neighborhood. Conclusion and broader impact. The discovery and ongoing study of 3I/ATLAS represents a remarkable achievement in modern astronomy and demonstrates the power of international collaboration in advancing our understanding of the cosmos. From its initial detection by the ATLAS survey system to the detailed follow-up observations by telescopes around the world, the investigation of this interstellar visitor showcases the sophisticated observational and analytical capabilities that modern astronomy has developed. The ability to detect, track, and characterize an object that originated in another star system billions of years ago would have been inconceivable just a few decades ago. Beyond its immediate scientific value, 3I/ATLAS serves as a tangible connection to the broader galaxy and the countless planetary systems that populate it. In an era when most astronomical discoveries involve distant and abstract phenomena like black holes, dark matter, and exoplanets that can only be studied indirectly, interstellar objects provide a rare opportunity to directly examine materials that formed around other stars. The organic compounds and volatiles preserved in 3I/ATLAS literally represent samples of another world that have traveled across interstellar space to reach our cosmic neighborhood. The study of 3I/ATLAS also demonstrates the importance of maintaining and improving astronomical survey capabilities. The object was initially missed in several survey images before its eventual discovery, highlighting the challenges involved in identifying rare and unusual objects among the vast numbers of more common targets that such surveys detect. The lessons learned from studying 3I/ATLAS will help improve future survey strategies and analysis techniques, potentially leading to earlier detection of future interstellar visitors and more comprehensive studies of their characteristics. As 3I/ATLAS continues its journey through the solar system and eventually returns to interstellar space, it will carry with it the distinction of being one of only 3 confirmed interstellar objects that humanity has ever observed. The data and insights gained from studying this ancient wanderer will continue to influence our understanding of planetary system formation and evolution for years to come. Future discoveries of additional interstellar objects will undoubtedly build upon the foundation established by the study of 1I/Oumuamua, 2I/Borisov, and now 3I/ATLAS, gradually revealing the hidden population of objects that drift through the galaxy, carrying with them the secrets of distant worlds and ancient cosmic events. The story of 3I/ATLAS ultimately illustrates both the vast scales of space and time that govern our universe and the remarkable ability of human curiosity and ingenuity to reach across those scales to uncover fundamental truths about our cosmic environment. As this ancient visitor from another star system continues its passage through our solar neighborhood, it reminds us that we are part of a dynamic and interconnected galaxy where materials and objects regularly travel between star systems, connecting distant worlds across both space and time. The continuing study of 3I/ATLAS and future interstellar objects will undoubtedly yield additional surprises and insights that will further expand our understanding of the galaxy we inhabit and our place within the vast cosmic community of planetary systems that surrounds us.